Alright, so in the last video we basically talked about Pascal's triangle and the expansion of x plus 1 to the power of n. We tried a few terms as I showed you over here, and we saw similarities between Pascal's triangle and the expansion. So, and then we talked about combinations and basically what they were. And so in this video I will try to explain how combinations basically come into effect in sort of determining what the expansion of a binomial is. So let's basically get back to the binomial, like Pascal's triangle again. So this is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay. And what we're going to do is I'm going to call this row right here, because remember how we said that this was x plus 1 to the power of 0. So in other words, the n term, the exponent right here, is n equals 0. So I'm going to say that's n equals 0. In this case, the next term will be n equals 1, because it's x plus 1 to the power of 1, n equals 2, and it's x plus 1 squared, and I'm going to call this row n equals 3, which is x plus 1 to the power of 3. And it's kind of convenient because if you see n equals 1, we only see 1s here. If you see n equals 2, this starts with 2, the middle term is 2. If it's n equals 3, you know, the second term over here is 3. So it sort of kind of makes sense, and it's a little bit intuitive. Now, let's, one thing I guess looking at 0 and 1 aren't really interesting. Let's look at 2 and see why this is 1, 2, 1. So say if I were to expand this, right? In other words, this would be x plus 1 times x plus 1. And if you sort of expand this, what you really get, so I'm just going to just look at this term right now, it's going to be x squared, because x times x, and then we're going to be like there's 1x over here because x times 1, and then this term times there, it's 1x plus 1. So in other words, what we have are two x's. We have two x's. So we have two x's over there, and so basically we need to somehow collect all the x's and basically figure out, I mean, this would be so hard to do if we had to expand each time. So we need something sort of to help us count the number of x's. Let's try x plus 1 cubed. Let me just scroll down a bit. So let's do x plus 1 cubed, which is basically x plus 1 times x plus 1 times x plus 1. Right? So let's do the first, let me just combine the first two. So basically we get x squared plus 1x plus 1x plus 1. That's basically what we had previously, because this is just basically x plus 1 squared, the first two terms, times x plus 1. And now let's sort of multiply that out again. So we get this term times that, so it's x cubed. And then we get plus 1x squared plus 1x squared plus x. And then now we have to multiply all these terms by 1. So we get plus x squared plus 1x plus 1x plus 1. So basically what I did was I took each of these terms and multiplied by x over here, which is how I got these first four terms. And then I took each of these and multiplied by 1, which is how I got the last few terms. So if we sort of collect the like terms, we get x cubed, and then we see that we have 3x squared. So I'm just going to write x squared plus x squared plus x squared. And then we see that we have 3 x's, so we have plus x plus x plus x plus 1. And so if I scroll down just a little bit more, what I get is I have x cubed. There are 3 of them, so I have 3x squared. There are 3 of them here, so I get 3x plus 1. So what we really need is, if we are expanding this and we want an efficient way of finding what the term is, in other words, we pretty much want to go from here to here directly, we need some much more efficient way of counting how many x squares there are, how many x's there are, so we can just directly jump from here to here. Okay? So in order to do that, what the discovery really is that what I showed you before, the n choose r, right? this really helps us count that. So this really helps us count that, and I'll show you how. So once again, I'm just going to write this as n factorial, r factorial, n minus r factorial. And what I really recommend is that on your GDC, figure out what the combination is. So this is actually another way of writing this is basically NCR. So there are two notations. You can write it this way, or you can write it that way. And for many calculators, if you look for this, you can figure out how to basically punch this into your calculator. So for example, in my TI 83 or even 84, if I did 5NCR, if you look for that command 3, what basically this means is 5 choose 3, and it's just equal to, let me do 2 because that's what I did in the previous example. So let me do 2 over here. So if you looked in the previous video, that's what I used. So, and if you plug this into your calculator, you will get 10. All right, so the question still begs the question, how does this help count? So let's go back to Pascal's triangles. I'm just going to draw it out again. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, right? And remember how I said this was basically the first row is n equals 0. The second row is n equals 1. The third row is n equals 2. And this fourth row here is n equals 3. Okay, so what's important to remember is that in sort of each row, the first term, we're going to sort of classify that as 0. So let's look at, for example, this right here. So if we look at 1, 2, 1, okay? So this is n equals 2, right? The r term over here, the first one is r equals 0. So basically, what's important to remember is that for each of these, the very first one basically starts with 0. The r term here is equal to 1, and the r term here is equal to 2. So let's basically use the n choose r and figure it out. So in this case, this is n equals 2 and r equals 0. So if you look up 2 choose 0, right, and if you just basically punch this into your calculator, you will see that this is equal to 1. Okay? Let's try another one. If you try this second one over here, so we know that n is equal to 2 and r is equal to 1. If you do 2 choose 1 and you plug that in, you will get 2. Okay? If you do 2 choose 2, which is this final term over here, because n equals 2 and r equals 2, remember this is equal to 1. So remember, this is n choose r. Okay, so let's try, for example, let's try another row. Let's try 3, 3, 1. Okay, so let's try this one. So this is n equals 3, and remember, this is r equals 0. I'm just going to extend the page a little bit. This is r equals 0. This is r equals 1. This is r equals 2. And this is r equals 3. Okay, so remember, this counting thing, this n choose r, all it's doing is it just helps us count how many of like the variables that we have. So in other words, remember when we went back to this example, which was x plus 1 cubed, all this is doing, all the n choose r is doing, is helping us count how many of the x squares there are, how many of the x's there are, how many of the constants there are, and so on and so forth. That's all they're doing. They're just making that a little bit more efficient. And we'll see some examples later of how this comes into play, but let's just sort of go with this for right now. So, so that's that's n choose r. So let's look at this. So if we do 3 choose 0, so remember this is n. So this row is n, and then r is equal to 0. So 3 choose 0 should be 1. If you plug that in, you will see 1. 3 choose 1 is equal to 3. 3 choose 2 is equal to 3. And finally, 3 choose 3 is also equal to 1. So in other words, it just follows this pattern. 3 choose 0 is 1, which we see right there. 3 choose 1 is 3, which we see right there. 3 choose 2 is 3, which we see right there. And 3 choose 3 is 1, which we see right there. Okay? So let's, for example, try to predict what the fifth row will look like, or when n is equal to 5, okay? So let's say when n is equal to 5. And so if we want to know what that, what that sort of n equals 5 row looks like, basically we can start with 5, choose 0, and that should equal 1. And try plugging it in, you'll see exactly that. 5, choose 1 is equal to 5. 5, choose 2 is equal to 10. 5, choose 3 is equal to 10 as well. 5, choose 4 is equal to 5. And let me just scroll down here a little bit, see if I can get everything in view. Yes, I can try. I'm just going to do it here. 5, choose 5 is equal to 1. So let's see if this is right or not. So we can just draw Pascal's triangle and figure out if that's true. So it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And let's see this row. So it's 1. Okay, so we got that one. 5. Yep, we got that one. 10. Yep, we got that one. This is 10. Yep, we got that one. We got 5. Yep, we got that one. And finally 1 over here. Yep, we got that one. All right, so basically this is how Pascal triangles emerges, and now we've figured out a way for any given row that we can determine what the numbers are. In the next video, I will show you how this is useful for any expansion and how we can use basically this combination to determine what the expansion of any binomial is. So stay tuned for the next video.